Yeah, so my name is Philippe Gamet. I'm with CNES and CESBio, Centre d'études spatiales de la biosphère. I'm TRISHNA project scientist, which means I'm in charge of coordinating the science team activities. And my background includes flight dynamics and physics of optical measurements. So I'm here to talk about TRISHNA, and I will I will start with the water issue, some very brief introduction. I will not go into too much detail. Then the TRISHNA mission design, and a small focus on evapotranspiration retrieval. So you got some things about the context by Zoltan previously. So we have a lot of pressure on energy and food coming up, a lot of pressure on biodiversity, and of course global warming, which means that we need reliable metrics that have to be homogeneous a long time and on every scale from global to regional. Just some figures about water use and agriculture. Globally, 70% of water use is for agriculture. And this number goes up to 80, 90% in arid regions. So that's how it's very important to rationalize the use of this water, especially for agriculture. Just one map provided by FAO. It's a projected water scarcity in 25 and in the coming years. And you can see that the intertropical region is really in the first row facing these water scarcity issues in the coming years. So India is concerned, so it's really relevant to build a mission with India. I'm quite sure you have the background about the water cycle. We are going to deal with this evapotranspiration variable, which is the way the surface gives back water to the atmosphere in the water cycle. I will skip this. So TRISHNA mission design, it's a cooperation between the French and Indian space agencies. The launch is expected at the end of 26, so it's quite soon. We have a 5 to 7 years lifetime. You have here a sketch of the system design between France in blue and India in orange. So France is basically responsible for the thermal infrared instrument, and India for the bus, the visible and shortwave infrared instrument, and the control ground segment. We have two payload ground segments, one in France and one in India, and we're going to share the world, but the product distribution will be global. The design drivers of the mission are the ecosystem stress and water use, and also the coastal and inland waters. But of course, as soon as you have high resolution, high revisit thermal infrared data, you can also address urban heat island, the cryosphere, and solid Earth. Solid Earth is also a topic that is worth mentioning, because there are some studies showing that by analyzing thermal anomalies of the surface, you can actually anticipate volcanic eruptions. So that would be that is a very interesting domain. You've seen the global coverage, the coverage here on the top right. So all continental surfaces and coastal areas. So this acquisition mask is harmonized with LSTM. So we make sure we cover all areas of interest. With TRISHNA, we have a 3-day revisit because we only have one satellite, not like LSTM. So you have here a sketch showing, this sketch was shown by Albert Olioso, a typical temporal pattern of acquisitions. This is over Italy. So you can see in black the Landsat acquisitions, in red the TRISHNA acquisition, in blue the LSTM acquisitions. And on the bottom, you have the uncertainty of daily evapotranspiration, the uncertainty that is induced by interpolation. And you can see that with the 16-day revisit of Landsat, the uncertainty is between 1 and 2 millimeters per day. And with TRISHNA alone, you can get under 1 millimeter per day. And of course, when you get LSTM and when you get combined data from TRISHNA, LSTM, and SBG, this uncertainty is expected to be reduced. TRISHNA's ground resolution is 60 meters, so this is important to access to typical field scales in Europe. What is particular to TRISHNA is that we decided for a mission design that allowed to have different observation angles, up to very high angles, 38 degrees, and this will allow us to explore the directional anisotropy of the thermal infrared signal, which is still a research field. You can see here that close to geometrical position that we call the hotspot position, we have a very strong variation of land surface temperature, and it's important to obtain data, to model this, and to account for this. We decided this for TRISHNA because in the intertropical zones, so typically in India, you can have up to 3 months a year where some significant part of the swath are affected by this hotspot phenomenon. So the performance of the LST retrieval is degraded in these conditions. So by having different observation angles, we actually have an 8-day cycle, and we use an extended swath to have at least three acquisitions per 8-day cycle. So we make sure that anytime and everywhere you have at least 2 acquisitions in 8 days that are out of the hotspot conditions. The overpass time, it's the same than LSTM. So Zoltan said 1 p.m. in Europe. So this means 12:30 at equator. So we have harmonized our overpass times between LSTM and TRISHNA and SBG. So we all 12:30 at equator. So that implies 12:30 in the night for thermal infrared acquisitions also. The spectral bands, we have 7 bands in the solar domain and 4 bands in thermal infrared. So I'm not going into details here unless you have questions. And the NEDT at instrument output is 0.2 K, which is more than sufficient to get 1 Kelvin accuracy in land surface temperature. We have a free and open data policy, just like the Copernicus data policy. Level 1 are top of atmosphere reflectances and brightness temperatures. Level 2, ground and water reflectances, land and sea surface temperatures, and emissivities. And one specificity of the TRISHNA ground segment is that we will also provide level 2B and level 3 products, level 3 being continuous time series of daily evapotranspiration. And as Zoltan said, we are cooperating with ESA and with NASA and the Italian Space Agency to harmonize our products, even our ATBDs, the orbits, and GALVAL campaigns. So that's the whole the mission design of TRISHNA in one slide. Now a small focus on evapotranspiration. So I think you will have a lecture about evapotranspiration later today, but so this can be like an introduction. So it's a key variable to rationalize the use of water for irrigating agriculture. So as I said, the objective with TRISHNA is to deliver a continuous time series that provides every day the best possible estimate of the field scale daily evapotranspiration, because that's what is needed for decision making for irrigation every day. having an estimation every day. So this, with TRISHNA alone, of course, this implies a lot of interpolation, extrapolation. But then when LSTM data come, when SBG data are there, we can fill these gaps with more and more data. So that's why the harmonization between the missions is important, because no mission alone can provide this everyday land surface temperature. So I'm sure you had some lectures about the radiative transfer equation in the atmosphere, how we get level 2A products. So we get land surface temperature, we get emissivity, and the reflectance on the surface. But then we are going to work on another equation, which is the surface energy balance equation, which is the way we compute the net radiation at the surface. So we have a first way of expressing the net radiation, which is by accounting for the inputs and outputs of energy fluxes at the surface. So for this, we use here in blue the downward solar radiation, RG, and the downward atmospheric radiation, which is in thermal infrared. And if you have this way of expressing the equation, you can also have the second way, which is that this net radiation divides into sensible heat flux, which is the way this energy is used to heat up the surface. You have the latent heat flux, which is the way plants, which is the way the energy is dissipated into evaporating water. And you have the ground heat flux, which is the way the energy is dissipated into the ground. The way we're going to work here is that we are going to express the latent heat flux, which is related to evapotranspiration, as a residual of this equation once we have computed the other terms. So sensible heat flux is computed from the land surface temperature it's actually related to the gradient between the air temperature and the surface temperature, and ground heat flux is related to vegetation variables. So for all of the terms of this equation, you can see that the land surface temperature is a major forcing variable. I want to focus on one aspect of these products, which was evoked by Zoltan also previously, is that the timeliness is really a critical feature for these data. You can see here on this sketch, if you see time is on the horizontal axis, that when a healthy crop faces water deficit, it results in a stomatal closure to limit the water losses. The fact that a plant closes its stomata results in stopping the exchanges with the atmosphere, not to lose too much water. But the result of this is that everything is stopped, including photosynthesis. So the plants will heat up, and this will be detectable in the visible domain after maybe a few days, maybe 1 week. When the plant turns yellow. But this will reduce in reduced matter production, and this will reduce on the degradation of the status of the plant. On the other hand, as soon as the plant closes its stomata, the plant heats up, and it is detectable with thermal infrared. Immediately, within minutes, it's detectable in thermal infrared. So that's very different from detecting it from visible data. So you can decide to supply water, and then the stomata will reopen, and you don't lose any production. Because the stomatal closure and reopening is a reversible phenomenon, and that occurs every night. Most of the plants close their stomata every night and then open them in the morning. So that's really reversible. So you can. That's why we want to work on this surface energy balance equation and not only on visible data. So latency is really one of the key features of these missions. I will conclude with a few take-home messages. So evapotranspiration, it's the largest water loss component of continental surfaces. Daily field-scale time series of evapotranspiration are the products we want to deliver with TRISHNA, and it's really the key to rationalize the use of water for irrigated agriculture. It can be estimated as a residue of the surface energy balance equation, and land surface temperature provided by these satellite missions is really a major forcing variable. I hope I have convinced you that timeliness is really critical for delivering these data. Besides agriculture, many science and applications will benefit from this high revisit, high resolution, high performance global surface temperature measurements. There are lots of challenges, physical challenges, to deal with the thermal infrared signal. It's affected by turbulence. There is the directional effects that you have to account for. There is the pixel heterogeneity that has to be accounted for. So lots of issues to deal with. Also separate emissivity from temperature, accounting for topographical effects in mountains. So still a lot of work. There are also technical challenges, which I'm not going to detail here, because building this kind of thermal infrared instrument is a challenge. Calibration and validation will obviously benefit from international synergies. And TRISHNA is going to be launched in 2026, so it's of course the front runner of this new generation of satellite missions. Okay, it's all I have. So thank you very much for your attention. I don't know if I have time to take some questions, or you can always email me.
Thank you, Philippe. Yeah, I guess 2026 is coming up quite soon, so we're all really looking forward to seeing TRISHNA data. We do have time for some questions. If anyone in the room has a question for Philippe, or everything was already answered before in the LSTM presentation, maybe? Yeah. Yes.
Can you actually turn the camera to the room, or?
I don't think that we can, no.
Okay, too bad.
Because
Because I'm just seeing a wall basically right now.
We'll take a picture for you and send it to you.
Yeah, please do.
Jans, you have a question?
Yeah, I do. Thank you very much for that really interesting presentation, Philippe. My question is about the viewing angle and the risk of seeing the hotspots at certain viewing angles. Will there be when creating the level 2 data sets, because it's still an open question about how to operationally validate data at these wider viewing angles, will there be nadir only products, like with the level 2 data, or level 3 products? Will there be a flag to just warn end users that, okay, this is being taken at an oblique angle? It may have physical processes that aren't present in a nadir view.
Thank you for the question. I mean, it's a very important topic, and it's a very big issue. Actually, LSTM will also have different view angles because when you go up in latitude, then you get more observations, and definitely the user will want to use these observations. So everyone will actually have directional effects. So what we will do with TRISHNA is provide let's say the reference LST product as is, with its directional effects, because people working on assimilated LST in hydrological models are also working on accounting for this directionality. So that's the first thing. But on the other hand, we're also working on how to model this directional anisotropy, and will include as a research product this corrected LST, which will be, let's say, normalized to nadir LST. but this is just a research product. The important thing to do is to provide the user with an uncertainty and the performance of this product. And this is very challenging because actually the shape and amplitude of this hotspot depends not only on the geometrical aspect, but also on the meteorological conditions, on the scene content, but also on the water status of the plant, which is the very variable that you want to estimate. But what we know for sure is that far from the hotspot, this effect is quite limited. So you can have a first order model of this directional anisotropy that you can account for, and you know that the performance is still good as long as you're far enough from the hotspot, which is what we want to do with TRISHNA, is say we flag the data saying, okay, you're far away from the hotspot, so you can use the data and the performance is good, or you're too close to the hotspot. We have a model to correct, but the performance is degraded. And we really count on the first TRISHNA data, let's say the first year in orbit, to help improve the models of directional anisotropy. And obviously, this will be used in LSTM. I don't know if I answered the question, but it's a research field, actually. So there's a lot of work, and we have some high-test data of last year that we are going to use also to improve the models of directional anisotropy.
Sorry, Philippe, we're just having a fire alarm.
Oops.
You actually do. Okay, it's finished.
Before I was interrupted, I was going to say response. It's just that operationally we don't have multi-angle regular.
I can't hear you. I mean,
the microphone just
it stopped just after a multi-angle.
Yeah, so we don't have many in situ radiometers currently around the world that have the capability of measuring at multi-angles. So operational validation will be limited to these like one-off campaigns that like the one at KCL that in the presentation yesterday by Martin Worcester. Will there be funding to expand existing or setting up new stations that have these that will try to measure the hotspot directly or the directionality in order to validate the model? Because it seems like we only have very limited observational data to test your model and validate the data currently.
Yeah, I mean that's correct. We are going to increase the instrumented sites, especially in Lacro in France and in some other sites to try to capture this. But the issue anyway is that I mean LST is affected by turbulence, so you have to have different angles at the very same time to be able to separate what comes from changes in the wind to changing in the direction. So that's why we also count on the high-test data that was acquired last year. I don't know if the data are now have been processed and available. Maybe Jennifer will know about this because that was these data were acquired simultaneously. So we hope we can get some information about the directionality of the signal. We also have used data from a master campaign, which is which occurred some time ago in California, and then we initiated some modeling with it. But you're right. I mean, the lack of data is quite obvious. So we're going to have some instrumented sites about this, but obviously not enough. But as I said, dealing with rejection anisotropy far from the hotspot conditions, geometrical conditions, is, I mean, the effects are not so high, except in some very typical, like in vineyards or rural, rural agriculture. Well, Jennifer knows about this, but most of the time it's limited in its impact. So that's how we're going to deal with it. But obviously that's a big issue: the lack of validating data.
I see. Thank you very much.